This is the second part of Chapter 2 involving chemistry. It goes into some more detail of biochemistry, and I may break it down into two sections. There's a lot of slides here, so this PowerPoint will go into more of the chemical composition and reactions of living matter. And so we can start by kind of breaking chemicals down into either the inorganic or organic compounds. Generally, inorganic compounds don't have carbon, and organic compounds do. Organic compounds and macromolecules are four main classes, including carbohydrates, fats, proteins, and nucleic acids. And for fats, a lot of times we'll call them lipids. And so a lot of times these contain covalent bonds, and inorganic compounds include things like water, salts, and lots of acids and bases. So all of these are essential for life. Water is the most abundant inorganic compound, and it makes up about 2/3 or so of living cell volume. And so it has some unique properties that we talked about in part 1 that give it these different characteristics, like high heat capacity, where water is able to absorb a lot of heat and also release a lot of heat with little temperature change to the water. And so this helps to prevent sudden shifts in the temperature of the water. I always think about this when I go to the beach and it's May and it's 100 degrees outside, but the water hasn't yet caught up and it's really, really cold. Um, but in the body, that's a beneficial thing. We can take on a lot of heat without changing our body temperature too extremely. A high heat of vaporization is another characteristic of water, and this is when water is able to change from a liquid to a vapor, or to a gas, which is a vapor, and this takes a lot of heat, but it's used in cooling the body, and you could probably guess how: sweat. All right, water is also a polar solvent. So we talked about that in part 1. So it's able to dissolve lots of solutes, especially ionic substances. And so it's able to transport those substances too. We see it transport lots of different electrolytes, ions, and even, in A&P too, we talk about things like hormones that are transported through blood, which is a large part water. And so this characteristic makes it really, really ideal for parts of different transport systems. Water also has reactivity, so it's part of hydrolysis reactions and dehydration synthesis reactions, and it helps us with cushioning. For example, in the brain and spinal cord, CSF, cerebrospinal fluid, cushions those organs. So let's get back to salts for just a second. These are ionic, as we said, and so they can break down into smaller components in water. And they separate into cations and anions. And so this doesn't include hydrogen and hydroxide ions, just as a note. So these are electrolytes since they dissociate in water, because that can cause the movement of water between compartments in the body. And ions play a big role with different body functions, especially sodium, potassium. We'll see them later in the semester when we talk about action potentials and things like calcium and iron. So these drive the movement of water, and they influence not only electrolyte homeostasis, but also water homeostasis and fluid balance. So they're very important for keeping us healthy. Acids and bases are electrolytes too. They ionize and dissociate and break up in water. So let's talk about acids first. They have a pH that ranges from 0 to 6.99. They're known as proton donors because they release hydrogen ions, and hydrogen has an atomic number of 1, has 1 proton, so that's where that comes from. And so they are able to donate lots of hydrogen ions in a solution. Examples include hydrochloric acid. And so acids are on the low end of the pH scale, and the lower the pH, the stronger the acid. Bases, on the other hand, are proton acceptors. They pick up hydrogen ions, and they have a higher concentration of hydroxyl, or you'll hear me say hydroxide, ions. and those are pretty synonymous just depending on the textbook you use. So bases are important too. The pH of basic solutions is from 7.01 to 14. And some important bases include the bicarbonate ion. This is the way that 70% of our carbon dioxide is transported in the body, and ammonia. And we find bases and acidic substances in some household items, including food and drink, but also like household cleaners. So let's look at the pH scale for a second. We'll pull up the one from your textbook, and this scale is logarithmic. So what does that mean? It means that we multiply the pH, or not the pH, but the concentration of ions by about 10 between each of these little segments of the scale. Let's go through a little bit more about that. I think I had the notes pulled up here. Yes, so here we go. This is a better explanation. The scale is logarithmic, so each unit, each pH unit represents a tenfold difference. So as an example, a substance with a pH of 5 is 10 times more acidic than a pH of 6, and it would be 100 times more acidic than something with a pH of 7. The more hydrogen ions that the solution has, the more acidic it is, and the lower its pH. The more hydroxyl or hydroxide ions it contains, the higher the pH and the more basic it is. Neutral solutions like pure water have an equal part of hydrogen and hydroxide ions, and their pH is 7. That pH is 7. All right. So make sure you know about the pH scale, be able to describe it for the exam for sure. Then there's buffers. Buffers help to resist changes in pH. And so buffers, if pH is really, really high and alkaline, and we're talking about, let me give you an example here. Where does this happen, right? If blood pH, which normally has a pH of 7.35 to 7.45, but let's say that it's way higher than that, then buffers in the blood can release hydrogen ions, and that will help to pull the pH back down toward that normal range. If the person is in a state of acidosis and their blood pH is below 7.35, then buffers can help by binding the hydrogen ions, and that will help to bring the pH back up toward that normal range. And so by doing this, buffers can help to convert strong acids into weak acids, strong bases into weak bases. And this is super important. In A&P 2, you normally talk more about buffers, and there's two big physiological buffers, which are the respiratory and the renal systems. And then there's other chemical buffers too, like the carbonic acid bicarbonate buffer system. All right, so why do we care about pH and maintaining pH? Well, in the body, if we change the shape of things, we change their function. And I'm really sorry about that, like chainsaw in the background right now, not planned for this afternoon. Okay, but if we change the pH of our blood too much, it can denature proteins or change their shape, and then they lose their function. And proteins have all sorts of important functions. So if they change and they can't work effectively anymore, then it can hinder lots of body processes, and this can lead to complications with various body systems and could even lead to death in some really extreme cases. Okay, so let's talk about organic compounds a little bit. They all contain carbon except for carbon dioxide, and some other substances that are inorganic technically. Carbon is electroneutral, so it shares electrons, but it doesn't gain or lose them. So it's really easy for carbon to form covalent bonds and share electrons with other elements. And the major organic compounds, which I refer to often as like the big four macromolecules, are carbs, lipids, proteins, and nucleic acids. Sorry again about the background noise. These macromolecules are polymers, and poly means many, and so they're repeating units of building blocks called monomers, mono for one. And so as we go through the next little bit, we'll talk about the building blocks of each of these macromolecules. These are broken down in hydrolysis reactions, but they're put together and made in dehydration synthesis reactions. So I'm not going to test you too intensely on those processes, but just make sure you generally have an understanding of how these are made. And let's go into some more detail about each of the four big macromolecules. So carbohydrates are first, and they include sugars and starches. They have carbon, of course, hydrogen and oxygen, and the hydrogen and oxygen are in a 2-to-1 ratio. And there's a few classes of carbohydrates. Mono, again, is one, so these monosaccharides have one sugar. Monosaccharides are the monomers or building blocks of carbohydrates. When we string monosaccharides together, let's say we have two of them, we get a disaccharide. And if you had three or more together, technically that's a polysaccharide. And so, what can carbohydrates do? What's the purpose of this? Well, monosaccharides include things like glucose. And so these are very, very important. Blood sugar is very important for helping us with an energy source, and carbohydrates are a great short-term energy storage for the body. Disaccharides include things like sucrose, that's table sugar, maltose, and lactose. And these are big sugars, too big to pass through the plasma membrane of cells. And so this picture shows us the typical kind of common disaccharides. Polysaccharides include things like starch and glycogen. Glycogen is the way that we store sugar in the liver with the help of insulin. And starch is the carbohydrate storage that's used by plants. All right, so these are not very soluble as far as carbohydrates go. I'm not going to include pictures of the molecular structure of these on tests just to kind of ease any fears there. But carbohydrates, just for a second again, help out with things like short-term energy storage. Lipids also provide energy, and they provide the most energy per gram compared to any other macromolecule. So they also have oxygen, hydrogen, and carbon, but less than in carbohydrates. And sometimes they've got some phosphate. And so these are insoluble in water and include these classes: triglycerides, phospholipids, steroids, and eicosanoids. For triglycerides, these are called fats when they're solid and oils when they're liquid. They're made up of fatty acids, 3 of them to be exact, bonded to a glycerol molecule. And so those are the building blocks or monomers of lipids, fatty acids, and glycerol. Triglycerides are super important for energy storage, and they also provide protection and insulation. If we were to look at their makeup, we could see kind of the molecular and almost structural representation here of a triglyceride. Moving on, we're going to talk about briefly saturated fatty acids, because triglycerides can be made of those, where all the carbons in the lipid are linked together by one covalent bond each, and so that results in a molecule with the maximum number of hydrogen atoms that it can hold. So it's fully saturated. And so this includes things that can pack kind of closely together at room temperature, like animal fats and butter. And just to give you an idea of what that looks like, we don't see any double bonds there. With an unsaturated fatty acid, however, you have one or more carbons that are linked together with some double bonds. And so it creates this kinked-like structure. And I removed that picture, but these are liquid at room temperature. And so that includes things like plant oils, like olive oil, and that sort of thing. And there's that noise again, I'm sorry. All right, phospholipids are a modified triglyceride, and they also contain glycerol and fatty acids, and they have different regions. So phospholipids, let me just show you a picture of what they look like as I move to another place. Phospholipids have heads and tails, and we see them specifically within the phospholipid bilayer of the plasma membrane of cells. Phospholipids heads are polar, and so they're able to interact well with water. They're hydrophilic, but the tails are nonpolar and they're hydrophobic, so they're not able to interact well with water. And that's a really good setup for the cell membrane that we'll see in chapter 3. So this is another representation of the phospholipids. And in the cell membrane, the plasma membrane of the cell, these are present in a double layer and the tails face each other. Next up are steroids. These are made of 4 interlocking ring structures, and so one of them includes cholesterol, which is super important for lots of different things in the body, including some hormones and also things like bile. So more to come with that later. The cholesterol is made by the liver and then found in some animal products. But steroids include, like I said earlier, hormones, but also the material that helps out with initiating, or not initiating, but the process of the formation of vitamin D, and also bile salts, which are parts of bile. Steroids are also present in the plasma membrane, especially cholesterol, which helps to stabilize the plasma membrane and provide it with some more support. So here's an example of steroid. You can see the 4 rings there. And then we're at eicosanoids. So these are derived from fatty acids that are in the cell membranes. And so this includes things like prostaglandins. You'll see prostaglandins come up, especially in like the reproductive system. These are found in things like sperm and or semen, sorry, and they're helpful, at least in that body system, to encourage uterine contractions. And so it's thought that they help to move sperm along and enhance reproductive success. That they're also present in other body systems and areas. So they play a role with blood clotting, maintenance of blood pressure, inflammation, and we talked about contractions. So that brings us to proteins, and I think I'll leave off here for another video just to break it up a little bit. So I'll be back with actually a part 3.